I can. So, good morning, everybody. We can start now the second session of this morning, and so it's me. I'm talking about nanoparticles for biomedical applications, and our talk is here. I think two days ago we discussed about the definition of the nanoparticles, some similarity in the history of the nanoparticles, and the structural aspect of the nanoparticles, and their characterization, the methods of their characterization. And today we will see the synthesis of nanoparticles. We will focalize on the synthesis in the distribution of nanoparticles, such as metal and metal oxide nanoparticles. And we will see in part the properties of the nanoparticles, how the thermodynamical properties, the nanoproperties change after size changed. And we focalize today on the optical properties of the nanoparticles. We will see briefly the optical properties and its dependence on the size for the gold nanoparticles. And tomorrow we will see the magnetic properties of oxide nanoparticles, magnetic nanoparticles, the possibility to surface modification of nanoparticles, the possibility of vectorization and targeting. We will see which requirement need to achieve to nanoparticles may be used for biomedical applications. And we will see rapidly the principle of MRI diagnosis and magnetic liquid hyperthermia tomorrow. But today we will start by the synthesis of nanoparticles. I should note that for the most of applications, there are the applications desired, such as information storage, biomedical applications, catalysis. The nanoparticles should present a controlled size. It means that we should control the variation of the nanoparticle size, and we should be able to produce the nanoparticle of desired size and change the size as we want. This nanoparticle should present a controlled shape, controlled chemical composition, of course, controlled structure, of course. Those nanoparticles should be monodisperse. I remember that the definition, the relative definition of the monodispersity is that the standard deviation is less than 5%. And this monodispersity is important for numerous applications. For instance, for magnetic resonance imaging, the monodispersed nanoparticles present higher relativity than the polydispersed nanoparticles of the same size. Those nanoparticles should present controlled surface state, and for instance, very important, especially for biomedical applications, because for biomedical applications we should craft some ligands at the surface of the nanoparticle in order to provide biocompatibility and provide the circulation of the body. So those nanoparticles should present tuning properties, different desired properties such as optical, magnetic, catalytic properties. They should be not expensive, stable in air, and present also controlled aggregation state. There are three approaches in order to design the nanoparticles, to provide the nanoparticles. There is in the synthesis in the solid state, the synthesis in the gas phase, and the synthesis in solution. The first synthesis in the solid and in gas phases are relatively expensive and present several drawbacks, which we will see rapidly later, and usually need enormous devices. And the synthesis in solution is relatively simple, not expensive. This is the synthesis by chemical methods, which usually need the use of molecular precursors. So let's start by the synthesis in the solid phase. The first approach, the first strategy is the synthesis on the substrate by using lithography by electronic beam, nano-impression lithography, photolithography, epitaxial molecular beam, atomic layer deposition. I cited just a few of them, but there are a lot of. The advantages of the synthesis is the nanoparticles with uniform size and a regular distribution on the substrate. Here you can see the same photograph of silicon nanowire obtained by epitaxial growth on the substrate. But those synthesis, those methods have numerous limitations, numerous inconveniences, which are the small quantity of the nanoparticles which may be obtained by this method, because we use usually 10 electronic beam in order to cut the surface of the objects. And there are also post-growth difficulty to treat those nanoparticles, and also non-metallic and semiconductor nanoparticles work very well with those methods, but the metal oxide nanoparticles present some difficulty, and a very small utilization of those methods have been reported for metal oxide nanoparticles. It's due to the use of relatively soft conditions which are incompatible with the production of metal oxide nanoparticles. So the first strategy is just mechanical reduction of the size of the big, larger size objects. So the mechanical methods in the solid phase is the industrial way, and we can obtain a very large quantity of the nanoparticles in comparison to the previous methods. But of course there are inconveniences such as some default in the obtained nano-objects. There are the problems with reproducibility, because since the mechanical methods is in order to the size reduction, so it's evidence. We also have a relatively bad control on the surface state, and also it is quite impossible to obtain small sized monodispersed nanoparticles by the mechanical methods. What happens in the gas phase? The synthesis of nanoparticles in the gas phase need the use of complex reactor technology. I can cite some reactors, such as flame reactor, hot wall reactor, plasma reactor, laser evaporation reactor, and others. You can see here an example of the photograph of the flame reactor, which is one of the common reactors to produce an important quality of the nanoparticles of high purity. Here you can see the schematical representation of this large device. Here is the burner with the temperature range between 1000 2400 degrees of Celsius. The filter, here the product, vacuum pump of gas, etc. So the installation is relatively complicated. The flame here is used to provide the energy to decompose the molecular or metal chloride precursors. The precursors here may be used in the liquid, gas, or solid phase, and I'm told that the used temperature are relatively high. And by this method we can provide nanoparticles from few nanometers to 500 nanometers of high purity. The advantages of all those synthesis in the gas phase is that we can obtain the nanoparticles with uniform surface distribution, with controlled surface density. Also, we obtain the nanoparticles, the nice nanoparticles, with the absence of surfactants on the surface. But I make this fact in the advantages, but may be inconvenient. For instance, for biomedical applications, we should interact the surface of the nanoparticles with different ligand, and for the nanoparticles provided by this method, this is not possible. So the disadvantages is first one, the price, because those are very expensive methods with special reactors, and also the impossibility for surface modification with ligands, which gives the method very this method not so good for different applications. So we arrive to the synthesis of the nanoparticles in solution, the synthesis used by chemists. The advantages are following. First of all, this is the simplicity of the synthesis. Chemical methods, we need just a flask, the refrigerator, the thermometer in order to control the temperature, and we inject here the precursor in the reaction dish. By this method, we can provide a wide range of the nanoparticles, such as metal quantum dots, metal oxide nanoparticles. We can achieve a good size control, and we can obtain the monodispersed nanoparticles and various monodispersed nanoparticles that have been reported to date. This method gives a relatively good yield for the nanoparticles. This method achieves a good shape control. These are not expensive, and we have a possibility to surface modification. Also, that is very important. Also, we have the possibility to dope the nanoparticles and obtain the partial nanoparticles or mixed nanoparticles in which the concentration, the quantity of one of metals may be homogeneously, may be distributed either homogeneously in the nanoparticles or gradually, and we can obtain different kind of doped nanoparticles. And also we can obtain the alloy nanoparticles. So before starting the synthesis of the description of the synthesis of the different kinds of nanoparticles, we will see the four mechanisms of the nanoparticles. There are four mechanisms such as nucleation, growth at the nanoparticles surface, oscillatoring, and saturation or fusion. This graph illustrates the presence of those four mechanisms, showing the variation of the precursor's concentration as a function of time. The precursors may be a molecular precursor, a nanometallic precursor, or just metal salts. So we start by injection of our precursors in the reaction flask, in the reaction mixture. First of all, in this reaction mixture, produce by reaction the nucleus of our nanoparticles, and the concentration of our precursor will decrease. So this first mechanism called nucleation. As the concentration of precursors achieve certain nucleation threshold, the growth on the surface will replace the first nucleation mechanism. This second growth on the surface means that the size of the previously formed nucleus of the nanoparticles will increase by the reaction of the molecular precursor with the organic precursor at the surface of the nucleus. And of course, the concentration of the molecule of the precursors will decrease. And as the concentration become small and at equilibrium, the child phosphoryltryptase mechanism will be organized. So this mechanism means that the small nanoparticles will be solubilized in the solution, and the large nanoparticles will form. We can also eat that the large nanoparticles eat the small nanoparticles. And at the final saturation state, saturation phase, there is a fusion between the previously obtained large nanoparticles in order to provide the formation of large micronucleic particles. So now we will see in detail those four mechanisms. And the first mechanism, the nucleation, may be heterogeneous or homogeneous. The heterogeneous nucleation is the nucleation at the surface, and this is not the object of my lecture. And the homogeneous nucleation is a nucleation in solution without interface with solid, via chemical reaction between precursors, which produces a nucleus of nanoparticles. To generate the homogeneous nucleation, we should work in saturated solutions because those solutions are not energetically stable, and the homogeneous nucleation is thus thermodynamically programmable. And so, I remember you that during this nucleation process, the concentration of precursors will decrease. The free energy of our reaction, delta G, is the sum of two delta G. The delta G of new volume, of new obtained volume, and delta G of new obtained surface. And for spherical nanoparticles, the delta G may be expressed as the delta G of new volume as minus 4 divided by V. V is the molecular volume of nanoparticles, PR cube, where R is the radius of nucleus, Boltzmann constant, temperature, and logarithm of S, where S is the ratio of saturation, plus the second term, delta G of the new obtained surface, as 4πr squared gamma, where gamma is the free energy of surface by unity of the air surface. So, if the saturation ratio S is larger than 1, delta G present a maximum. You can see here the variation of delta G as a function of R, and we can see the presence of maximum on delta G graph. This maximum of delta G is the activation energy for the nucleation process. And this maximum of delta G is arrived at R star, and R star we will call as a critical radius. And the critical radius R star may be obtained as the derivatives of delta G by the R equal to 0. And by using these derivatives, we can express R star from this formula as 2V gamma divided by 3KB T logarithm of S, which signify that the nanoparticles with the radius larger than the critical radius R star will be formed, the nucleus of those nanoparticles will be formed, and the nucleus of the nanoparticles with the radius smaller than R star will be sublimated. So the second growth mechanism, the growth on the surface of the nanoparticles, is operational after nucleation, when the precursor concentration decreases and become low, that a certain critical value called nuclear threshold, and the nucleation is finished, and the growing mechanism will play a preponderant role. As I told, in this second mechanism, the nanoparticles will grow by growing on the surface until the equilibrium concentration here is achieved. And here, the second growth mechanism will be finished, and the type osteotropic mechanism will be operational. So, a homogeneous size distribution is achieved for the short nucleation time, and if the small monodispersed nanoparticles may be obtained by rapid stop of the reaction at this stage, or by addition of precursors in the reaction mixture in order to keep the solution at saturation. So, if we stop the reaction at this time, we obtain monodispersed nanoparticles. And we avoid the osteotropic mechanism, which will broke nanoparticles and will obtain after the polydispersed nanoparticles. So for osteotropic mechanism, the large nanoparticles will grow, and the small nanoparticles will solubilize. And given that the saturation ratio S will decreases because the concentration of precursors will decreases, the R star will increase. Okay, and now we cannot operate with this R star, but we should recalculate another R star, which we will call R star prime. Thus, the nanoparticles with the radius larger than R star will grow, and the nanoparticles with R smaller than the new R star prime will solubilize. And for this reason, we said that the larger nanoparticles will eat the nanoparticles and will grow. So, if we stop the reaction at this stage, if we precipitate our nanoparticles, we cannot obtain monodispersity. Okay? And generally, we obtain double size distribution with the large nanoparticles with the R equal to around R star prime, and also the small nanoparticles. Okay? And if the nanoparticles continue to grow, if they don't stop the reaction, we'll obtain very large micrometric particles. Because micrometric is not nanoparticles. So the final Prof mechanism fusion is operational at the end of osteogenesis, and after growing on the surface, there is a secondary growth, growing by aggregation with other nanoparticles, and we can see the fusion of larger nanoparticles obtained in the osteogenesis mechanism, and we obtain the micrometric crystals. So, in order to obtain stable nanoparticles, first of all, we should obtain the core of the nanoparticle by chemical method, but it's not enough. We should stabilize this core of the nanoparticles by using different stabilizing agents, or we should insert our nanoparticles into the microscope. Now, in this second part, we will see various examples of the synthesis of metal and metal oxide nanoparticles in solution. And to the synthesis of those nanoparticles, there are two approaches which work relatively good. The first one is the reduction of metallic salts or molecular precursors containing metal ions. This reduction may be obtained either by using of reductors, chemical reductors, either by electrochemical reduction, irradiation, etc., etc. And the second possibility is the thermolysis, the decomposition of organometallic precursors, where metals have their degree of oxidation equal to 0. And this is a very good method which works very well for produce metal and metal nanoparticles with very narrow size distribution. So we will see. We will see now all of them. The first one is the synthesis of nanoparticles by reduction. So the precipitation of metals from aqueous or organic solutions need the chemical reduction of metallic cations. We can see here classical semi-reactions of reduction of metal ions, which take an electrons and decrease its oxidation state to 0. And here we can see the oxidation of reductant. And here the reaction which summarizes those two semi-reactions. So we can use different classical reductors such as H2 hydrogen, gaseous hydrogen, 8BH4, where A is the alkaline metal, hydrazine hydrate, hydrazine dichloride, different ions. And as I told, this reaction may be achieved, may be performed in water or in organic solids. The second strategy, the thermolysis, or the splash decomposition of organometallic precursors, is usually used for the synthesis of metal nanoparticles, but also metal oxide nanoparticles. The organometallic precursors are usually chosen to contain a metal in 0 oxidation state. The classically used precursors are metal carbanions, such as MCON, where M is a transition metal ions such as iron, cobalt, molybdenum, uranium, etc., etc. We also can use the respective clusters of those carbonyl, such as MXCOY, various for iron metal ion, iron 2CO10, iron 3CO12, etc. Those carbonyl are commercial, or the same for cobalt, molybdenum, uranium. So, by thermolysis of those carbonyl or those precursors in solvent with high boiling point, such as diffuse ether, anisole, etc., usually in argon or nitrogen atmosphere, we decompose the ligand and we obtain the metals in zero oxidation state and the ligands which usually state conserved in the surface of the nanoparticles. This reaction usually performed at high temperature at around 250 or 300 degrees Celsius. The same methods, the same strategy we can use to obtain metal oxides, but now by thermolysis of the molecular precursors, we obtain at the first stage the metal nanoparticles, metallic nanoparticles, and after, by control oxidation in air or in the presence of oxygen, we can form the metal oxide nanoparticles. The metal oxide nanoparticles may be also synthesized from different other organometallic precursors in which the oxidation state is not zero, but certain is not zero. And the classically used organometallic, it's not organometallic, coordination complex precursor is M-acetylacetonate of transition metal ions. Transition metal ions has iron, cobalt, nickel, etc. And by thermolysis of those precursors, now in air, because we don't need nitrogen or argon atmosphere, we obtain the metal oxides. The advantages of this flash decomposition is that we obtain the nanoparticles with controlled stoichiometry, with controlled size, monodispersity, and those nanoparticles are soluble in organic solutions. This last point may be important and may be inconvenient for biomedical applications, because the nanoparticles for biomedical applications should be soluble in water, because we are aqueous. So after this synthesis, we should exchange the ligand and pass to the aqueous solutions. But we will discuss about this after. Another synthesis, the tight synthesis to provide the metal oxide nanoparticles, maybe also via co-precipitation of precursors. This is a very classical method usually used. There are two mechanisms, olation and oxidation. In the first one, in the olation, the metal complexes, aqua and hydroxy metal complexes, form the coordination bond through the hydroxy bridge, hydroxy ligand, and one more water molecule goes out. In the oxidation mechanism, both hydroxyl complexes of metals form together the coordination bond through oxygen bridge, and also water molecule goes out. goes out. I would like to cite here a very famous Massard's method in order to obtain magnetite or ferrite, bulk materials, or nanoparticles. In order to synthesize those materials, we should take precursors, iron salts, iron 3+ and iron 2+ fluorides in stoichiometry 2/1, 2 equivalents of iron 3 and 1 equivalent of iron 2+, in basic media with the pH equal ranging from 8 to 14. In order to provide the hydroxy complexes, information of hydroxy complexes, and so heating, we perform this reaction by co-precipitation via olation and oxidation to form the magnetite bulk or nanoparticles. If we want to obtain ferrite, we just instead of iron 2+, we will take bivalent metal ions such as manganese, copper, nickel, etc. And this reaction is obtained in the same way. This reaction is running in the same way. So it's very important to stabilize the nanoparticles because after nucleation and forming on the surface, we can obtain the aggregation of the nanoparticles. So we should stabilize. So an addition of stabilizing agent or also insertion of those nanoparticles into the different matrices is needed to obtain the nanoparticles and avoid their aggregation. I put here two types of stabilization. The first one is the use of different ligand polymer surfactants, which provide the design of nanoparticles in colloidal solutions. And the second one is the use of inorganic matrices such as silica, glasses, organic matrices such as copolymers, and in this way we obtain the nanoparticles. So let's see the stabilization in solution because it's the object of our discussion. The objective of the stabilization is to cover the surface of the nanoparticles with thin films of stabilizing agent, ligand, polymer, or surfactants in order to avoid coagulation. So the stabilizing agent, the nature, should recover totally the nanoparticle surface and not partially. It should be attached at the surface. The best way is covalent attachment, covalent grafting, but the absorption will also work. In order to avoid the displacement of the shell during the Brownian motion. Okay, it's very important for biomedical application because we use our shell in ramp. It's very important. So the thickness of the thin film should be larger than 3 nanometers in order to avoid coagulation of the nanoparticles because the dipolar energy should be lower than kBt. So if we represent here 2 nanoparticles, the distance, the minimal distance between those 2 nanoparticles, between their surface, should be larger than 6 nanometers. it is important to see that the volume concentration of the adsorbed molecules at the surface of the nanoparticles is held weak to keep the diffusiveness of the layers. And if the layers of the molecule shell are too dense, we can obtain the van der Waals interactions between those molecules, which will provide, which will induce the flocculation of the nanoparticles, and this flocculation will induce their aggregation. So this slide is just to show you very classical stabilizing ligands. The very classically used stabilizing ligands. Usually we have two parts of in those ligands. The first one is the binding group, and the second one is the longer outlet chain. So this binding group will coordinate the surface of the metal on the outside in order to give a covalent linkages with the surface, and this long chain will diffuse. So we can cite spermine, malic acid, octylamine, dodecylamine, hexadecylamine, octadecylamine, stearic acid, etc., etc. We can use acid with alkyl chain or amine with alkyl chain alone, works. But we also can use the mixture between the acid with long alkyl chain and with amine with alkyl chain, and this way provide very good stabilization. As concerns the stabilization by polymers, this is very important for our nanoparticles in view of biomedical applications. So I will describe the stabilization more in detail. The first and very simple way to stabilize nanoparticles via polymers is just absorption of polymers at the surface of the nanoparticles. It's very simple, but it's not very efficient because the polymer is not covalently linked to the nanoparticle surface. This polymer may be displaced, in the glue, for instance, we can obtain naked nanoparticles which will aggregate, so it may be damaged. The second way is the covalent grafting of polymers at the nanoparticle surface, which give relatively good results. Here now the polymer is covalently grafted, covalently linked to the polymer. Usually the polymer has two parts. The first part is the binding group to nanoparticle surface, and the second part is the hydrophilic region. So the binding group will be attached to the surface of the nanoparticles, and the second hydrophilic group will diffuse. I present here the polymers which are soluble in water, okay, in order to stabilize our nanoparticles. So we will obtain a nanoparticle soluble in water. So it works relatively well. The binding group, this binding group depends on the nanoparticle surface, and this is a hard and soft acids and base theory, which will told us which binding group we should use for which metal oxide surface. for instance, the iron, cobalt nanoparticles, nickel nanoparticles, or their respective oxides, maybe obtained and maybe stabilized by carboxylate groups, phosphate, phosphonate groups. But if you want to stabilize the gold, platinum nanoparticles, it's the best way to choose the choice group. So carbon acid for hard base and sulfuric acid for soft bases. So another way is also they use here the binding group, providing the halide effect of this binding group with multi-dentate coordination groups. So you know that halide effect coordinate in the best way the nanoparticles in the surface nanoparticles, and this stabilization seems to work better. The use of amphiphilic micellar ligands in water also has been reported for nanoparticle stabilization. Such polymer has also two parts, the hydrophobic region and the hydrophilic one. The hydrophobic region will stabilize the hydrophobic surface of our nanoparticles. These nanoparticles are hydrophobic, and the hydrophilic region will diffuse and provide the solubility in the water of our nanoparticles. Excuse me, sorry. So the final way also is they use a cross-linkable bifunctional ligand, which give relatively complex stabilization, and this way work very well. Such polymer has not two but now three parts. The binding group, as usual, the hydrophilic region, hydrophilic group, and also cross-linkable group. So the binding group will be attached on the surface of the nanoparticles, the hydrophobic region will diffuse, and the cross-linkable region together with the cross-linker will provide an additional stabilization of this device and will maintain the polymer construction in the best way. Just a few examples of usually used polymers. This is the PVP, PPO, PEG, with different molecular weight from 400 to 10,000 to 12,000, PPG, etc. And usually we functionalize the PEG polymer with different amino groups, phosphonate, carboxylate, etc., in order to provide the covalent anchorage of anchoring of the polymer in a nanoparticle surface. So now we will see several examples. Let's start by the classical metallic gold nanoparticles. So the metallic gold nanoparticles is very easy to obtain. The synthesis works very well, and usually we can very easily monodisperse or at least the nanoparticles with narrow size and distribution. the generality of this reaction is very simple. The precursor HiUCl4 with reduction, the reduction of of the gold at gold 3 class provide the gold at oxidation state 0 nanoparticles. In organic solvents or in water, we use relatively soft reductors such as hydrogen, ABH4. We can also use sodium citrate, etc. The first Churkevich method gives the nanoparticles usually soluble in the water. Very simple method. We dissolve our precursor HiUCl4 in water. The solution is yellow. We heat the solution and we add the sodium citrate. We stir and the solution becomes deeply red, which signifies the formation of gold nanoparticles. The submarine reaction is presented here. The role of the sodium citrate is double. The sodium citrate here reduces the gold salt in metallic gold and also stabilizes the formed nanoparticles by negative charge. And we can adjust the size of the nanoparticles. We can play with the size of the nanoparticles by varying of the sodium citrate concentration in comparison to the gold concentration, the precursor of gold concentration. You can see here the 10 photograph of obtained gold nanoparticles by using this method by Churkevich, which present the size distribution ranging from 10 to 20 nanometers. And here we can see interesting varying of color of those solutions depending on the nanoparticle gold concentration. We can see that in diluted solutions, diluted nanoparticle solutions, the color is yellow, and as we concentrate our solution, the color becomes red. And this phenomena we will see during our discussion about the optical properties of gold nanoparticles. The second synthesis of gold in organic solvents, either by Prost method or by Schmidt method, provide very small nanoparticles with very narrow size distribution. I show you two examples. We start with HiUCl4 precursor, and by using bromide of tetraethylammonium, and which is a reductor and also stabilizing agent. A stabilizing agent, and with NaBH4 as a reductor, we obtain the nanoparticles with the size ranging from 1 to 4 nanometers. This reaction is operational in toluene or in other solutions. The second one, the Schmidt method, give very narrow sized nanoparticles with the size equal to 1.4 nanometers. With our HiUCl4 precursor and by reaction with triphenylphosphine, we obtain firstly the molecular precursor, the intermediate molecular precursor with triphenylphosphine. This is a complex gold ClP3, and then we will reduct this intermediate precursor, and we obtain the nanoparticles with very narrow size distribution with 55 atoms overall. Here you can see the comparison of the 10 images obtained by Turkevich method here, and here by evolutioned methods in organic solvents. You can see that in water we obtain relatively large nanoparticles, not homogeneous in size and in their shape. But in organic solutions we obtain small nanoparticles with size non-viscosity, and those nanoparticles stabilized here by Ludican theory. This table gives some examples of metallic nanoparticles, or the synthesis of metallic nanoparticles in aqueous solutions. For instance, we can also cite the methods of synthesis of gold with trisodium citrate, but we can use also mercaptopropionate as stabilizing agent, and this synthesis gives the best results as previously mentioned the Turkevich method, and we provide relatively good nanoparticles, small nanoparticles with the size ranging from 3 to 5 nanometers. The platinum also may be synthesized from H2PTCl6 precursor by using this reductor, and also by using this stabilizing agent. We obtain narrow size distributed nanoparticles of 1.5 nanometers. The silver nanoparticles from AgNO3 with the size ranging from 3 to 5 nanometers, etc. Here we can see some example of the synthesis of metallic nanoparticles in organic solvents. For instance, we can cite also the synthesis, the design of the gold nanoparticles in formamide or in THF from HUC4. The reductor are formamide and NADH4 respectively, and the stabilizing agent here is the polymer, and here the solvents, THF, which play a double role. This is a stabilizing agent and solvents. The silver nanoparticles, very nice silver nanoparticles obtained in ethylene glycol, stabilized by PVP. I can show you these 10 images. Those nanoparticles, cubic nanoparticles, very nice, ranging with a size ranging from 50 to 100 nanometers. I can also cite the synthesis of ruthenium nanoparticles from wrinkled coat by in THF or another solvents with hydrogen as reductor and stabilized with polymers or link. But I remember that Moscato told me about this synthesis 2 days ago, so I'll jump, and I'd like just to show you the high resolution transmission microscopy, electronic microscopy images of those nice ruthenium nanoparticles with the size 1.4 nanometers, stabilized by PVP. This is the work of Bruno Chouret groups from Toulouse. So, the second example is the synthesis of metal oxide nanoparticles, especially focalizing the synthesis of magnetic metal oxide nanoparticles. The first example is the iron and cobalt nanoparticles. I remember you the previously mentioned slide. we will obtain our nanoparticles from organometallic precursors by using the carbonyl of transition metals in solvents with high boiling point by decomposition thermolysis of those precursors. So the first example is iron nanoparticles obtained from pentacarbonyl of iron by using stabilizing agent, the mixture of oleic acid and oleoamine with the heating at 287 degrees of Celsius. You can see here those nice nanoparticles, dispersed nanoparticles of 9 nanometer. The pathway for the decomposition of iron pentacarbonyl has been mentioned in this publication. This pathway is relatively complicated and not well defined. There are formation of different clusters such as iron 2 CO9, iron 3 CO12, etc., etc., and different conditions of reaction will highly influence the formation of those clusters and then influence the size of final nanoparticles. So it means that it's very difficult to say the pathway and predict the size of final nanoparticles if we change the temperature, if we change the reaction conditions. Another example is bimetallic alloy nanoparticles such as iron platinum, which can be obtained by thermolysis of two precursors. Our precursor pentacarbonyl of iron, which should provide iron nanoparticles, but in this way we add also acetyl acetonate of platinum, and the decomposition of both should provide the synthesis, the formation of alloy nanoparticles, iron platinum. We use oleic acid and oleoamine mixture as in the previous case. The temperature is 300 degrees of Celsius, and given that the platinum here is not in zero oxidation state, we use a reductor and to become diol. And we obtain the nanoparticles of 4 nanometers, as we can see here from this STEM image and this HR10 image on the right. The third example is synthesis of metal oxide nanoparticles such as manitite. Focus on manitite synthesis. Also from pentacarbonyl precursor, but now in air, because we don't need protect because we want to form the oxide by using just oleic acid with the temperature 150 degrees and 250 degrees. This is a plateau. In diphenyl ether, we can obtain also nice nanoparticles of 14 nanometers by using this method following this publication. The same way is operational for cobalt-3 or 4 nanoparticles by using very closed conditions. in oleic acid and heating in difinil ether, we can obtain the nanoparticles of cobalt 304 of 9 nanometer, as we can see here from the STEM and Asher-TEM images. So I'll give you some references for the synthesis of magnetite nanoparticles of different sizes. It should be noted that we cannot rationalize the thermal decomposition of, for instance, iron carbon precursor in order to obtain nanoparticles with the increasing size. We cannot do this, it doesn't work. In order to obtain the nanoparticles of this size, we should play with the nature of precursor, with the conditions, and it's relatively hard work. So, in addition to the previously cited works, I can add the synthesis of 4 nanometers nanoparticles from acetylacetonate of iron with oleic acid and stabilizing agent. If we want to increase the size, we should change the precursor. We should use iron carbonyl, and we can obtain the nanoparticles of 10 nanometers. If we want to increase again the size, we change the precursor, and for the nanoparticles of 18 nanometer and 24 nanometer, we can use iron oxide hydroxide and iron oleate precursor. So actually in laboratory we use also pentacarbonyl precursor at high temperatures stabilized with oleic acid in docosane as solvent, and we obtained the iron oxide magnetite nanoparticles of 100 nanometers, which is relatively cheap. Here some references to the synthesis of ferrite and iron 203. Thus, manganese and cobalt ferrite have been synthesized following this publication from respective carbonyl metallic precursors. In this case, we take the mixture of iron carbonyl and manganese carbonyl, or iron carbonyl and cobalt carbonyl in oleic, and by using oleic acid as stabilizing agent with relatively high temperatures. So the example 4, which I would like to show you, concern the synthesis of core shell type heterostructured nanoparticles by using 2 ways. The first example is the nanoparticles with the core of platinum and iron 203 shell. You can see here from the STEM image and Asher-TEM here the core, which is dark, and the shell, which is more dark because this is the shell of oxide, so the electronic density is lower. So those nanoparticles have been obtained by sequential decomposition of acetylacetonate of platinum, and after the formation of platinum, we decompose the pentacarbonyl of iron in order to obtain the shell of iron 4. The second example is the nanoparticles with cobalt iron alloy core, you can see here, and iron 304 shell. It's also the sequential decomposition of this mixture, and then the decomposition of acetylacetonate of iron in order to provide the shell of this biomedical core. So we will I finalized our synthetic part, and now we will see the properties of nanoparticles. And first of all, we will see the influence of size on the structure, morphology, and thermodynamical properties of nanoparticles. And after, I think today we can discuss also about the optical properties of nanoparticles. So, it's not surprising that the structure, the morphology, and the physical and chemical properties of materials may be highly influenced by the size of grain and may be very different in comparison with the analogous bulk system. And this phenomena called size dependence of nanoparticles. Two phenomena may explain the size dependence. The first one is the continuum, because the small particles behave as like a box in which the properties may exist or not exist. And for certain critical sizes, the properties will be dependent on the particle dimension. And the second phenomenon is the surface or interface effect. The surface contribution will be more and more important as the size of the nanoparticle decreases. And yes, 2 days ago we saw that, for instance, for the nanoparticles of 2 nanometers, around 50% of atoms are at the surface. So the surface energy will become a major contribution in the total energy of materials, and it is particularly true for the nanoparticles of small size, especially lower than 10 nanometers. I would like to show you some examples of some parameters which may be modified to this size. The first parameters, surface specific energy. This is evident that the specific energy of surface will increase as the size increases. But the second parameter, the cell parameters, the influence of the size on the cell parameters is not evident. Sometimes some modifications were observed with the size decrease, but it is really difficult to have to do concrete conclusions due to the small number of examples, because it's very difficult to determine the cell parameters in the structure of nanoparticles. Two phenomena, two explanations may be given for this modification of cell parameters. The first is the quantum confinement effect, which may be made for the very small size, around 1 nanometer. And this confinement effect may modify the electronic structure, and the electronic structure will evidently influence the cell parameters of the structure. I precise that it is available for very small sizes. And the second point also is that the surface state of nanocrystal may also act on the cell parameters. The morphology of the nanoparticles also change as a function of depending on the size, but the influence of the size is also not evident. the equilibrium shape of the nanocrystal may be different in comparison with the equilibrium shape of the macroscopic crystal. And in my previous lecture, we discussed that theoretically, from modelization, the more compact and the more stable shape for the small nanoparticles, around 15 atoms, is the icosahedron, and as a consequence, dodecahedron, because dodecahedron is a conjugated polyhedron for icosahedron. As the size increases, the icosahedron will transform to other shapes following this scheme. Here I give you an example for a face cubic centered metal which may present 5 different shapes because we start from icosahedron or dodecahedron, and by using the cuts, by cutting of the vertices of those polyhedron, we obtain quasi-dodecahedron or truncated icosahedron or truncated dodecahedron. Okay, and those are semi-regular polyhedron or polyhedra of Archimedes. So for FCC metal, the presence of the existence of 5 shapes are possible. However, for small nanoparticles, the energy difference between the shapes is very big, because the energy barrier between the shapes are very big, and the nanoparticles may take one shape and then they can change the shape and present in another shape. So, in reality, for the small nanoparticles, we can observe a kind of fluctuation of particle shape. It's a very funny phenomenon. I'll show you a series of H10 images for gold nanoparticles with FCC structure of 2 nanometers with 459 atoms. We can this series of images was taken in time under the electron beam. Okay. So we start by twinned FCC structure. After this structure, the shape was changed and become icosahedron. Icosahedron, it's changed to FCC twinned, then octahedron, truncated octahedron, icosahedron, twinned FCC structure, etc., etc., and the shape fluctuates in time continually. What about thermodynamic properties? The thermodynamic properties of nanosystems is deeply modified in comparison with analogous microscopic systems. It was previously published and demonstrated that for small-sized nanoparticles, for instance, for condensed solid system, the limited size is smaller than 0.01 micrometer, and for the gas systems, the limit size is smaller than 1 micrometer. And utilization of classical thermodynamical equations are not available. I'll give some examples, where the properties will modify as the size will decrease. For instance, the vibrational entropy increases as the size decreases, the specific heat increases, the melting temperature decreases, and the temperature of phase transition decreases. For illustrate this modification, I'll show you the variation of the melting temperature of the gold nanoparticles. Here we can see the variation of the melting point as a function of the gold nanoparticles radius. We can see that for the bulk materials, for the bulk gold, the melting temperature is equal to 1064 degrees of Celsius. And as the size, as the radius of the particles decreases, we observe decrease of the melting point, and as the radius of the nanoparticles become relatively small, here the nanoparticles of around 10 nanometers in diameter, we observe dramatic decrease of the melting temperature, and for the nanoparticles of 4 nanometers, we have the melting point at melting temperature at 500 degrees Celsius. And the variation of melting temperature for different metals may be estimated and calculated from this equation, where Tm is equal to Tm of bulk, 1 minus alpha divided by 2R, where Tm bulk is the melting temperature of the bulk material, this is usually known. R is the radius of the nanoparticles, which you can take from M measurements, and alpha is the constant of materials, which is special for each material. So now I call you back. So now we will discuss about optical properties of nanoparticles, and especially I will focalize on the gold nanoparticles. In my first lecture, we discussed about this lithioscope, which presents a relatively funny phenomenon. It appears green in reflection and red in transmission, and this phenomenon is due to the presence of gold and silver nanoparticles inserted into the glass. Here we can see 1 nanoparticles of gold, cubic nanoparticles of 50 nanometers. It should also be noted that the glass colored by inclusion of metallic powder particles have been widely used in Greece for fabrication of the arc object, and in Middle Ages for the fabrication of stained glasses, and this such fabrication is actually also operational. Another example. Here is the bulk gold material, and here we can see this gold, colloidal gold solution. It's clear that the gold material is yellow, and the nanoparticulate colloidal solutions is red, and also we can note that there is some emission, some illumination under the excitation by laser. Alors, what's happened? The role of the nanoparticles in this modification of the color of the optical properties has been elucidated only in 19th century by Michael Faraday. And those optical properties are the consequence of an appearance of the surface plasmon resonance for the both nanoparticles and for the nanoparticles. As concerns the optical properties in bulk metals, I show you here the classical diagram for electron energy for metals, semiconductors, and insulators. And you can see that the formation of the energy bands is shorter, and the electron occupy the energy levels until the Fermi level. So, in the case of the nanoparticles, the electrons are confined in the particle. It's not in ours. The electrons are not in the particle. The alternating electric field of the light will induce an appearance of the collective oscillation of conducting surface electrons, as we can see here from this schematical representation, and thus this collective oscillation of conducting surface electron is called plasma electrons. So the electronic density of each particle oscillates with the optical frequency and made an oscillating charge at the surface of the nanoparticles. Okay, it's present here, and this phenomenon induces an appearance of dipoles which oscillate in phase with the electron. And this collective oscillation of the surface conducting electrons, called plasma electrons, is called surface plasma. If the wavelength of the light corresponds to the wavelength of the surface plasmon, a resonance of the electrons is occurred, which is called the surface plasmon resonance. As a consequence, we obtain an absorption excitation near wavelength. We also obtain the reflecting light, which is minimal, quasi all quantity of light now is absorbed by the particles, and the surface plasmon resonance absorbed in the visible and infrared condition. It depends on the nature of the matter. So, for instance, the gold nanoparticles absorbed in the green region, and this green absorption gives the intense red coloration of gold nanoparticulate solutions, as you can see here. The optical properties of the nanoparticles depend on many parameters, such as the nanoparticle size, nanoparticle shape, the nanoparticle structure, because it may be homogeneous or partial, or homogeneous with graduate evaluation of the metal ions, the metals. Also, the nanoparticulate concentration, the environment of the nanoparticle, because the optical properties may be changed by the presence of matrices or organic solutions, or even different organic polymers or organic ligands at the surface of the nanoparticles. Sorry. I would like to show you several examples of showing the size dependence of the optical properties of different nanoparticles. And here, the first example concerns the optical properties of spherical silver nanoparticles. We can see here the spectrum, the variation of the transmittance as a function of wavelength for spherical silver nanoparticles. We can see here a series of peaks obtained for different sized nanoparticles, 2.2 nanometers, ranging from 2.2 nanometers to 11 nanometers to 11 nanometers. Those peaks appear at 410 nanometers, and we can see that the radius of the nanoparticles, as the radius of nanoparticles increase, the transmittance of the spectra, the transmittance increased. And in contrario, if the air increased, the absorption decreases. And we can see that the size reduction induces a strong increase of the absorption. Here, the second example concerns the shape dependence of the optical properties of silver nanoparticles. Only one peak here is observed for the spherical nanoparticles. This peak is occurred at 410 nanometers, and for instance, for nanorods, we obtain two peaks at 400 and 800 nanometers. This is the spectra. And in addition, the wavelength of those peaks will be modified as the shape of the nanoparticles modified. You can see the shift, for instance, for those nanorods, this spectrum. So there is a 200 nanometer shift between those peaks as the length of those nanorods increase. Here I show you a tiny example of concerning the optical properties of the gold nanoparticles as a function of their concentration. Here we can see the 10 image of those gold nanoparticles of 10 nanometers. Those are spherical nanoparticles, and here we can see a series of nanoparticle solutions. Here, diluted solutions presenting yellow color, and here we can see the red color for concentrated solutions. This fourth example concerns the optical properties of the golden nanorods as a function of their size. So, the spherical nanoparticles, so just in the precedent slide, are yellow or red. The color modified from yellow to red, but the nanorods, we can see here those nanorods, with very narrow size nanorods, the color changed from blue to kind of violet or yellow violet, as the ratio white length increased. So at the end of my lecture, I would like point out that the optical properties of the gold and silver nanoparticles are well used for their biomedical applications. For instance, selective laser photothermal cancer therapy and bacterial infection. The laser hyperthermia means the use of optical heating for ablation of tumor. The gold nanorods are used as therapeutic adjunct in hyperthermia treatment because the surface plasmon resonance absorption of gold nanoparticles is followed by the rapid conversion around 1 picoseconds of the absorbed light into heat. So we can heat with the gold nanoparticles. We irradiate the gold nanoparticles. We provide the gold nanorod absorbed and emits in the near infrared spectra, so it is very interesting for in vivo imaging and also for hyperthermia therapy, because for human and animal therapy it's better to irradiate in infrared. Also, those nanoparticles may be used in cancer cell diagnosis and imaging by using bioconjugated gold nanoparticles. And the intense surface plasmon enhanced scattering from gold nanoparticles makes them promising as optical probes and labels for imaging-based detection of cancers. One such technique for molecular-specific labeling of cancer cells is the immunotargeting of nanoparticles by conjugating them with antibodies, different kinds of antibodies to antigens overexpressed on the diasynth cells. I would like also to point out that the silver nanoparticles are actually used as antiseptic agents. So I think, yes, I should now. Muchas gracias for attention. Do you have some questions?
Yeah, I saw that it's very interesting in the optical properties where the pulsion is the shape side. Okay? But if I want to control or if I want to obtain the shape in the nanoparticle, what kind of method, what method, what can I do?
Okay.
Because in your presentation you said about the stability, you spoke about the stabilization, no? Okay, but okay, it's very interesting. Yeah, I know. My medical application is very interesting. But if I want to control, if I want to obtain the different shape in the nanoparticle, okay, in the chemical method, how I do in the chemical method? Or do you know any method that maybe I can use for obtaining that?
Okay. Thank you. It's a very interesting question, but. I'm not sure that I know how it works. No, it's it depends of what we do. First of all, for the small nanoparticles, the nanoparticles smaller than critical size. Critical size is different. For different materials, we can calculate the critical size from individual constants, etc. But in general, it's lower than 20 nanometers. Okay. For this critical, for those nanoparticles, lower than critical size, the shape is also spherical or quasi-spherical. Okay, because the equilibrium morphology, the equilibrium shape should be icosahedral. Then by cutting off the vertices, we obtain numerous polyhedrons, but the shape of these nanoparticles tends to be spherical. Okay? After the critical size, the structure of the bulk materials will influence the shape of nanoparticles. And it is very difficult to say if I want to obtain this triangle, I should utilize this temperature, this precursor. This is completely empirical. Okay. For instance, for iron oxide nanoparticles, I'm working a lot for iron oxide nanoparticles, for magnetite nanoparticles. We can obtain spherical nanoparticles or cubic nanoparticles because magnetite presents cubic structure. Okay, so we cannot obtain another shape that cubes. Okay, or it is very difficult. So then we should maybe utilize some electric crystallization or another very not really chemical methods in solution. Okay, for the gold nanoparticles, it's quite different because by empirically, by varying conditions, precursors, we can obtain triangles, spheres, cubes, etc. Okay, but it is a very interesting question, but I'm not able, and I think nobody able to answer which how we can rationalize this completely.
I have two questions also about synthesis. I'm sorry.
You show that the graph is the point made versus the point made versus the size of the number. No?
The
And you
melting
say
temperature, the melting temperature.
and you show that the equation and Tn equal, okay, whatever. But in that equation, you show that the alpha is a constant.
Yeah.
Okay. From that alpha, what kind of the information, what can I do from alpha physical?
Where you can find the constant.
Yeah, from that physically, what kind of information can I do from that constant?
It's typically empirical.
Okay.
Okay. So you can find the alpha in the internet, but
Okay.
it's depends on the nature.
In the synthesis method, you talked about gas-phase methods, and you said that one of the limitations was that you couldn't modify the surface of the nanoparticles. So, is there any problem with synthesizing metallic or oxide metallic nanoparticles and then functionalizing it? Is there a difference between that and functionalizing it in the same method as the synthesis?
I'm not specialist in the gas phase method, but I remember that the surface of less nanoparticles not comprehend because it's specific. So less nanoparticles are in solid, and not in solution. We can disperse hardly less nanoparticles in solution. So quantization won't work.
And I have another question. Maybe it's a silly question, I don't know. For biomedical methods, you need solubility of the nanoparticles. But if you do this in chemical methods, you are synthesizing in a soluble media. So for me it was like a contradiction, because when you grow crystals in solution, they have to be not soluble in that medium.
Yes, but it's not a problem. It's not an limitation, because Prof, I'll talk about that tomorrow. Very, I think it's a very nice way. It's to obtain the nanoparticles in organic solvents. Instead of obtaining the nanoparticles with very narrow size distribution, it works very well. It is the best, the organometallic way by plasma composition is the best way in order to obtain narrow size nanoparticles. Because by co-precipitation you can obtain the nanoparticles in water, we can stabilize those nanoparticles with polymer, but the size distribution is not so good. And then we can exchange the liquids on the surface, and the nanoparticles will take the solubility of the liquid. Okay? It's very usual method for the gold nanoparticles. We can obtain the nanoparticles through the end, and then by using phase transition management, we can remove the nanoparticles from organic solvent, from fluid, and water with different freedom. And I will show you tomorrow an elegant way that we use in our laboratory in our nanotite. First of all, we obtain nanotite by this synthesis by plastic composition with the mixture oleic acid and oleamine, and then we craft the sugar or the surface of the nanoparticles, and given that the carboxylic acid are not covalently part of the surface of the nanoparticles, we use phosphonate works, and we